Hi, welcome to my talk about the chapters Why Rovers in Space Project Management of the book Planetary Rovers, Robotic Exploration of the Solar System by Alex Ellery. First, I'm going to talk about the first chapter, what are rovers, types of rovers, and classification by mass. And then to get to the second chapter, I'm going to talk about why a project structure and also the project procedure. So first, what are rovers? Of course, rovers are spacecraft, and they have been designed to explore planetary environments. This is especially hard because the planetary environment is often unknown, so you basically have to guess what will be right for the given planet. Also, they contain multiple subsystems, and the typical distribution of mass of a rover is with 30% for the chassis, 20% for scientific instruments, and 50% for the subsystems. Also, rovers face severe limitations because, of course, you have to send a rover to space via a rocket, so there's a huge mass budget in this process, and as a result of that, also a power budget. Because either we have to produce the power in the rover itself via solar or nuclear power, or you have to implement a battery and charge the rover in a, for example, a docking station or something like that. And because of the huge mass budget, there's just not much room or much mass left for this power budget to be huge. As a result of that, we have limited computational resources just because of the low power available. To face these severe limitations and to master them, they undergo a series of design phases, but I'm going to talk about that later in the second part of my presentation. Let's get to the different type of rovers. First, there are robotic autonomous vehicles. These are vehicles or rovers that can operate by themselves and don't need the help of Earth or humans in general. These are also the types of rovers you've heard about most in the last 10 years by the media. An example for them would be Perseverance, which has been sent to Mars in 2020, and its goal was to search for ancient life and gather rocks and soil. Then there are Taylor-operated vehicles, and these vehicles cannot operate by themselves. They have to be controlled by humans. In the example of Lunar 2, which you can see right here, they have been controlled from the Earth. This was the second Soviet lunar rover on the Moon, and it has been launched in 1973. Its goal was to collect images, observe solar X-rays, and measure local magnetic fields. Then there are human-operated vehicles which are unpressurized. An example for that would be the lunar roving vehicle used by the Apollo missions. And here you have a picture of it, but I'm also going to show you a clip of the rover in action.
Get me up to anything.
That's all, Mark. That max acceleration?
Yeah.
Man, you are really bouncing.
Is he on the ground at all? That's 10 kilometers. Huh?
He's got about 2 wheels on the ground. He's a big rooster tail out of all 4 wheels. And as he turns, he skids. The back end breaks loose just like on snow. Come on back, John. Hey, the deck is running. Man, I'll tell you, Andy's never seen a driver like this. Okay, when he hits the craters and starts bouncing, it's when he gets his rooster tail. He makes sharp turns. Hey, that was a good stop. Those wheels just locked. Mark off. Okay.
So as you can see in the clip, this is an electric vehicle which can be driven by 1 or 2 astronauts, and it was used in the Apollo missions 15, 16 and 17. Also, the design was mostly guesswork because there just wasn't much information around about the soil on Moon. This is also the reason why you can see these astronauts testing the vehicle, because they have to assess it. Last but not least, there are human-operated vehicles which are pressurized. This is only a concept, but an example would be Chariot, which you can see right here. And here the rover somewhat creates its own atmosphere, and this enables astronauts to operate it without wearing a spacesuit. And in general, one can say that manned missions are better, because Apollo returned a total of 382 kilograms of lunar rock, while the Russian missions only returned 0.32 kilograms. But of course, these missions are more expensive and also more dangerous, because you put the life of astronauts on risk. Then let's get to another form of classification, and that's the classification by mass. And this is interesting because all the rovers I've talked about until now were macro rovers with a mass of above 100 kilograms. So, for example, the Apollo lunar roving vehicle, which you have seen, had a mass of 210 kilograms. So right here you can also see the size comparison between Curiosity and Perseverance. So the latest two space rovers sent to Mars and the Tesla Model X. And if you're like me and you always thought of the size of a rover like these to be about the size of a bigger dog or something like that, and this is not exactly true. So here you can see it's rather or more the size of a car. But there are also mini rovers with a mass of 50 to 100 kilograms. An example for that would be Mars Kut, and it was a Russian Mars rover project which planned to launch in 1996. But in the end it was only used for experiments, and it resulted in a joint development of a remote control system by Russia and the US, so it wasn't just wasted resources. And these mini rovers basically do the same job as macro rovers, but scaled down. But there are also other concepts like micro rovers with a mass of 10 to 50 kilograms, and an example for that would be here the Canadian micro rover Kepwick with a mass of 30 kilograms. And this class is best for exploring because it has a really good balance of cost and range and also scientific payload. So typically here the range for a rover like this would be around 1 kilometer. And because they're smaller and just more affordable, they can be good if targeted to a high specific risk location. And here again, it's estimated that this class of rover offers 1/5 of the performance at 1/30 of the cost if you compare them to a macro rover. And of course, because they're so affordable, multiple can be deployed at once. And this is really good for either redundancy, like I said, for example, in a high-risk location, or also for rapid exploration if you just use multiple of these at once to explore the atmosphere. And then there's also the concept of nanorovers with a mass of 1 to 10 kilograms. And right here you can see a prototype of a nanorover which is only 20 centimeters long. And these can act as an extended robotic arm in combination with bigger rovers or lander, and basically just move around these bigger rovers or landers. And they're really effective because they can offload a lot of the communication and power generation, etc., to a loader, which results in a higher payload ratio for these class of rovers. Okay, that is everything for the first chapter. Let's get to the second chapter. And first of all, of course, there are many constraints in a project like this. So, for example, the constraints for Perseverance were a mass budget of 1,025 kilograms, the costs of $2.75 billion US, and the launch was scheduled for 30th of July in 2020. Of course, this is also a hard deadline because you can hardly reschedule the launch date. First, because you have to wait a few months before there's again a good constellation for a rocket to fly to Mars, and also because of the public opinion. Then to cope with these many constraints, of course, you need a large team. For example, this is the team behind Perseverance. So there are a lot of people which have to be managed and also be structured. And of course, with these big objectives, there come high expectations from the public. These projects are mostly funded by the government, so the public wants to see results. So for example, if the Perseverance mission had failed and $2.75 billion of taxpayer money would have been wasted, this wouldn't have been a good look and maybe would have led to the next mission having a lower budget. But even with the current resources, of course, there is not enough. So these have to be managed and assigned to the different parts of the rover. And to do all of that, of course, managers are needed. And of course, for these projects, we need a procedure. In a typical project, there would be 5 stages. First, the initialization, then the planning, the execution, the monitoring and controlling, and the closure of the project. But of course, this is not really feasible for our use case, because if you, for example, send a rover to Mars, it is 225 million kilometers away on average. So this stage right here becomes really hard because it gets really difficult to fix mistakes after. So there's a large emphasis on the second and third stage to avoid this. Then, of course, before you start a project like this, you need to set a goal. And because these projects are mostly government funded, the goals will be set by politicians. And a good example for that would be the following clip of JF Kennedy in 1961 in front of Congress.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
So why is this such a good example? Because not only it states a goal of landing a man on the moon and returning him safely to Earth, but it also sets a time limit, so before the decade is out. And after you've established a goal like this, the planning can begin. And the specifications can be established and you can begin with assessments and feasibility studies. And after that, of course, you have to start somewhere. And with a big project like this, the best tactic is to divide and conquer. So basically, you divide the project into multiple little projects, which can be, for example, the different subsystems. So here you can see the different scientific instruments of the Perseverance rover. These could function as sub-projects. And after every sub-project has made feasible progress, one can begin to develop the interfaces between the sub-projects. By doing that, multiple sub-projects can get combined to bigger projects. And after a while and after recombining and conquering the different sub-projects, the whole project as a whole can stand again. There, of course, the hardware and software of the top-level systems have to be developed. Of course, in this stage, there needs to be a lot of planning because the different subsystems cannot operate by themselves but overlap, and you have to define how these overlaps will be handled. Then the third stage, we come to the detailed design development and also the qualification activities of design and environmental performance. And this is basically just further planning and development. Then after that, you have to build the actual hardware and software and test it, of course. This is really resource heavy, and as you can see here is the peak in the required resources. And I will show you a clip on how NASA is doing this. So yeah, this is a lot of work, and basically this is the do or die part of the project, because errors here can lead to a failed mission. Then, after all these tests here have been completed, we get to the last stage where we launch the vehicle to space. But before the launch, we have to plan where the rover is going to land. And these landing ellipses get smaller and smaller because our technology gets better and we can more precisely define the landing zone. So right here you see a comparison between the different rovers sent to space. And while in 1976 the ellipse was 280 by 100 kilometers, the Perseverance rover had only a touchdown zone of 13 by 7 kilometers. And with this improved technology, we can target new areas which were previously too dangerous to land on. And this also allows for more precise pre-planning on where the rover is going to go after it has landed on the moon or planet. The landing of the rover, of course, is a really critical stage, and here many things can go wrong. Of course, this is also the stage which produces really interesting pictures for TV, and I'm not going to withhold them from you. In the end of the landing clip, you can also see the scientists cheering because now most of the dangerous parts of the mission is over and the rover has safely landed.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
After that, of course, we're not finished. We have to monitor the rover, and if there are mistakes or errors, we have to try to fix them from here. Or if this is not a possibility, we can try to learn from it for the next time. And of course, we have to monitor how the mission progress is going and which new things the rover can discover. And after that, basically, the mission is over, and so is my talk right here. Here are my image sources and also my video sources. And here are the rest of my sources if you want to do further reading by yourself. Either way, thank you for your attention and have a great day.